Hello, Chemistry 12. This is Mr. Chan. And today what I wanted to do was I wanted to talk about acids and bases again, but I want to talk about something called strong versus weak acids. So when we talk about acids or bases, we do talk about them being strong or weak. Now, when we talk about strong or weak, the strength of an acid is determined by the position of the equilibrium in the dissociation equation. Now, we use the word dissociation if we're looking at Arrhenius acid and base definition, or we use the term ionization equation when we're talking about Bronsted-Lowry. Now, what do I mean by this? So let's say if we were to take an acid. So let's say we had, I don't know, HA. Now, HA is just a general term for an acid. So we have our acid here. And when we add it to water, it is in equilibrium to produce H3O plus and A minus 1. So what you have is the H plus donating the proton to water. Now, so when we say it's a strong acid, what we can say is a strong acid is the equilibrium lies far to the right, or you get lots of product. So what we could say is that it is either complete dissociation or complete ionization. You have lots of product. A weak acid is where the equilibrium lies far to the left or near the middle of the equilibrium. What happens is there is not much dissociation occurring. Okay. Now, one thing I want to emphasize is this. When you think about a strong acid, the strength of an acid is not the same as concentration of acid. Strength of acid is talking about how far the equilibrium lies, whether to the right or to the left. Concentration of acid is talking about how much stuff is packed into 1 liter of solution. They're not necessarily the same thing. So you can have a very dilute acid that's very strong, or you can have a concentrated acid that's very weak. Okay, example would be like people that say, oh, you wear glasses, you must be smart. Wearing glasses has nothing to do with your intelligence. Wearing glasses just means that you are blind. And that's the same idea. Strength of an acid and concentration of an acid are two different things. Now, one thing you need to be aware of is the strong acid has a weak conjugate base and vice versa. So a strong acid has a weak conjugate base. A strong base has a weak conjugate acid. The example would be like spending. If you are a good spender, you are a lousy saver. If you are a good saver, you are a lousy spender. And for bases like acids, the strength is determined by how much it dissociates in water. Again, when we talk about strong or weak, we're looking at the amount of dissociation or ionization in water. Now, there is a table in your data booklet that sort of ranks some common acids that we deal with in Chemistry 12. Now, so in your data booklet, you will see this relative strength. Now, how do you read this? All the substances down the left-hand side, these are acids. Because you're reading from left to right, what happens is you are producing a proton. All the substances down the right-hand side, come on. are bases. Because if you read from right to left, what you are doing is you are accepting a proton. Now, notice there's a shaded area between sulfuric and hydronium ions. This barrier, everything that's highlighted in gray, these are considered strong acids. The reason being is you take a look at the arrow, there is complete dissociation. Everything below here and all the way down, these are considered weak acids. Because again, these are equilibrium. Okay. Now, you might say, well, Mr. Chan, how about hydronium ions? Hydronium ions is right at the border between strong and weak. Can we say that hydronium ion is a strong acid? The answer is no, because again, if you take a look, it is at equilibrium. It is strongest of the weak. Now, if you look down the right-hand side, again, you will notice that here, there is a separation. So in this particular case, right here, here you have the strong bases. And here, all the way to the top, these are our weak bases. Okay. Now, if you take a look, notice here there's a ranking system on the left-hand side. As you go further up on the left-hand side, when you're talking about the acids, you are going from a weak acid. So here, water is a weak acid. And as you go up further up to the left, perchloric is a strong acid. So there's a ranking. For bases, you look down the right-hand side. Notice water here is considered weak. And as you scroll down the strength of bases, it becomes stronger. Okay, so you notice that there seems to be an opposite effect. As the acid gets stronger, its conjugate base gets weaker, and vice versa. The weaker the acid, the stronger the conjugate base. So what we're going to do is in the next half of this lesson, we're going to talk about how to use this acid-base chart. Now, but before we do that, I just wanted to show you the difference in terms of separating strong acids and weak acids, and what does it look like? So remember, when we talked about a weak acid, what happens is that there's very little dissociation. So here what we have is our water molecule and we have our acid particle. Now, so for a weak acid, what happens is when they are mixed, the acid molecule donates very little hydrogens to water. So what you have is, it says here, a small percentage ionized. Notice very little ions in solution. Compare that to a strong acid. If you take a look at a strong acid, like hydrochloric acid in this sense, what happens is because it dissociates completely, you have lots of ions in solution. Now, what's the significance of the quantity of ions in solution from a strong versus a weak acid? Well, what happens is this. If we take a look here, so let's say we have a strong acid, okay? Now, lots of H3O plus ions in solution. Weak acid, not so much. Now, if we were to test the pH, notice for a weak acid, if I dip it here, the pH is acidic, maybe a 4 or 5. For a strong acid, if I dip it, it's probably like about 2 or 3. Not much of a difference. But the key thing is notice the amount of ions in solution. The surefire way to tell the difference between a weak acid and a strong acid, or a weak base and a strong base, is its electrical conductivity. So if I had a weak acid, notice not very many ions. If you look at the light bulb, it doesn't glow very well. If we had a strong acid, notice because there's lots of ions in solution, the amount of conductivity is a lot better, and you will notice that the light bulb actually glows brighter. So that's the surefire way of separating the difference between a weak acid and a strong acid is based upon its electrical conductivity. Now, go back here. So how do we use this table that I gave you? So if we go back to our notes here, okay. So it says, so far, we have dealt with acid or bases mixing together. What would happen if we had two acids mixing? So let's say, for example, I had HCO3 minus 1 and H2PO4 minus 1. Now, both of these have hydrogens in the formula. So in this case, both can donate H plus. Both can donate H plus. So what would be the products? Okay. Now, using the acid-base table, we can determine which reactant is the stronger acid, therefore tends to donate the proton more. So what do I mean by this? So if you took a look at the acid-base chart, you look for HCO3, which is right here on the acid side, and we have H2PO4. Now, both are on the acid side. So what you can do is you do a comparison. Which one is the stronger acid? Okay. In this case, you will notice that H2PO4 is higher up on the left-hand side. And so as a result, it is the stronger acid. So if we were to look back here, in this particular case, we would say H2PO4 is stronger. Therefore, donates more. So what that means is, if we were to look at the equation, we would have HCO3 minus 1 and H2PO4 minus 1. The hydrogen would be donated. And so what you get is you have H2CO3 and HPO4 minus 2. That would be your products. Okay. So what you want to do is you take a look at the acid-base chart, and you want to check out which one is the stronger acid, which one will tend to donate more. Now, the example would be something like this. Some of you may have been to large family dinners and everything is going well until it's time to pay the bill. And so what happens is when it's time to pay the bill for the big family dinner, people get into fights. I don't know if you've experienced this. You know, people try to outpush each other to, give their credit card to the waiter. And basically, whichever one is more stubborn or more aggressive will end up paying for the dinner. That's the same idea with this H2PO4 and HCO3 minus 1. They are both wanting to donate, but because the H2PO4 is better at donating, it will donate its proton more than HCO3. Now, some of you might say, but wait a minute, Mr. Chan, we see H2PO4 as a base, and we see HCO3 as a base. What do we do in this scenario? You do the exact same thing, but instead of looking for the stronger acid, you are looking for the stronger base, and whichever one tends to accept a proton more. In this case, HCO3 minus 1 is a stronger base, so therefore it will tend to accept the proton better than H2PO4, which we see right here in our notes. Okay, notice here HCO3 minus 1 accepted the proton. Now, we also have to take a look to determine which side is favored. We need to compare the acid on both the reactant and the product side of the equation to see which one is stronger. Now, recall back to last day. We said that there's always going to be two acids and two bases. An acid for the forward direction and an acid for the base direction. For the reverse equation. Same idea here. So in this particular case, if I were to rewrite this, we have HCO3 minus 1 and H2PO4 minus 1 will be in equilibrium with H2CO3 and HPO4 minus 2. In this case, this would be the base. This would be the acid going in the forward direction. And in the reverse reaction, this would be the acid, and this would be the base going in the reverse direction. So now what we need to do is we need to compare the acid for the forward direction and the acid for the reverse reaction. So again, using the table, what we can do is we can take a look at this. One moment. What we have to do is take a look at our acid-base chart and see, you do a comparison of the acid in the reactant and the acid in the product. So if we take a look at here at our acid-base chart, okay, again, what you want to do is you want to compare your H2PO4 versus your H2CO3. So in this particular case, you notice that H2CO3 is the stronger acid. So when we take a look at here, we have H2CO3 is stronger than the H2PO4 minus 1. Therefore, the reverse reaction is favored. And pushes reaction to the reactants. So when you're given a situation like this, we have to use the acid-base chart twice. Once is to figure out what our product is. And then secondly, is to figure out, once we figure out the products, which side of the equilibrium is favored. Is it the reactants or the product side? And for both situations, what we are trying to do is see which one is stronger. The first scenario, whichever one is stronger donates more. And in this case, whichever one is stronger, then we know which side the equilibrium favors. All right, folks, thank you very much. Have a good day. Bye-bye.